Have you ever stopped and wondered how scientists actually know if a new drug is working? Or how a company can be so sure that their big new marketing push was a success? Well, I can tell you, they don't just guess. They use this really powerful, super systematic process to tell the difference between a real effect and just a random fluke. And that process? It's called hypothesis testing. It's the essential bridge that takes us from a simple hunch to a decision that's actually backed by data. Today, we're going to walk through exactly how it works, piece by piece. Okay, let's kick things off with a scenario where the stakes are incredibly high. Picture this. A big pharmaceutical company has just poured years of work and, millions and millions of dollars into a new cholesterol drug. They run their first clinical trial, and the results, they look amazing. Patients are seeing their cholesterol levels drop. But, and this is the huge question, is the drug actually the reason why, or did they just happen to get a bit lucky with a specific group of people in their trial? Is this a genuine medical breakthrough, or is it just statistical noise? This is exactly the kind of critical question that hypothesis testing was built to answer. So when you strip it all down, hypothesis testing is really just a formal set of rules. Think of it like a bridge. Over on one side, you've got a small, manageable group you can actually measure and study. That's your sample data. And way over on the other side is the massive group you really care about, the entire population. Hypothesis testing gives us a safe, structured way to use what we learn from that small sample to walk across the bridge and make a really smart, calculated decision about a claim for that entire population. It's how we make big, important calls using limited information. All right, so here's our game plan. We're going to build this thing from the ground up. First up, we'll see how to take any question and frame it as a testable idea. Then, we're going to dive deep into the absolute heart of the test, the null versus the alternative hypothesis. From there, we'll have to face a hard truth, the risk of being wrong. After that, we get practical and actually run through the core steps. And finally, we're going to master the two main ways to get to a final answer, the super common p-value approach and the more traditional critical value approach. The very first step, before you do anything else, is all about framing your question correctly. We have to take a real-world question, something like, hey, is our new drug any better? And translate it into a formal, testable structure. This means we have to create two very precise, competing statements that together cover all the possible outcomes. And that right there brings us to the absolute core of every single hypothesis test you'll ever see. These two competing statements have names. One is the null hypothesis, and the other is the alternative hypothesis. And let me tell you, getting these two right is probably the most important part of the whole process, because literally everything else you do flows from how you set this up. The best way I've ever heard this explained is with a courtroom analogy. The null hypothesis is basically the defendant's presumption of innocence. It's the default position, it's the status quo, it's the belief that nothing interesting is going on. Just like a defendant is assumed to be innocent, we start by assuming our null hypothesis is true. The burden of proof then falls on us, the researchers. We're like the prosecutors. It's our job to gather enough convincing, overwhelming statistical evidence to make the case and say, hey, we need to overturn this initial assumption. We need to reject the null. Okay, let's get a little more specific here. The null hypothesis, which we write as H with a little subscript 0, or H naught, is the statement of no change, no effect, business as usual. Now, here's the most important technical detail, so listen close. The null hypothesis always has to contain some form of an equal sign. It can be equals, less than or equal to, or greater than or equal to. Why? Because we need that solid, fixed value to test against. On the flip side, we have the alternative hypothesis, or HA. This is usually what we, the researchers, are hoping to prove, that there is an effect, that something has changed. So its notation will always be a strict inequality, not equal to, greater than, or less than. These two hypotheses have to be opposites that cover all the bases. They can't overlap, and one of them has to be true. Let's make this real with a few examples. Say you're in manufacturing and you've got a new process. The null hypothesis, the status quo, is that this new method is no better than the old one. The alternative, what the engineers are trying to prove, is that it is better. For our cholesterol drug, the null is that the new drug has zero effect, that it's no different than a sugar pill. The alternative, what the company's banking on, is that the drug does work. Or for a sales team, the null is that a new bonus plan doesn't increase sales. The alternative is that it does. See the pattern? The null is always that boring, nothing's changed scenario, and the alternative is the exciting claim that something new has happened. Now, this is a really important point to understand. We are trying to make a huge decision about an entire population.
but we're only looking at a tiny piece of it, our sample. And because of that, we can never, ever be 100% certain that our conclusion is right. There's always a chance we got it wrong. The whole point of hypothesis testing isn't to magically eliminate that error, but to understand it, to quantify it, and to manage it.
This grid right here shows you the 4 things that can happen every time you run a test. Let's walk through it. Okay, so in the real world, the null hypothesis is either true or it's false. And based on our data, our decision is to either reject it or not. If the null is actually true, the defendant is innocent, and we correctly decide not to reject it, great, that's a correct decision. Same thing if the null is false, the defendant is guilty, and we correctly reject it, awesome. But those other 2 boxes, that's where we get into trouble. Look at the top left. In reality, the null is true, but our sample data happened to be really weird, and it led us to reject it. That's a type 1 error. It's a false alarm. It's convicting an innocent person. In business, they call this producer's risk because a factory might throw out a perfectly good batch of products because of one bad test. Now look at the bottom right. Here, the null is actually false, but our sample just wasn't strong enough to prove it, so we failed to reject it. This is a type 2 error, a miss. It's letting a guilty person walk free. This is called consumer's risk because it could mean a faulty product gets approved and shipped out to customers. Okay, so we know how to set up our hypotheses and we understand the risks involved. So how do we actually do the test? Well, the process is incredibly systematic. There are 3 key steps that will take us all the way from our initial question to a final calculated result. So the procedure is always the same. Step 1, just like we've been practicing, you clearly state your null and alternative hypotheses. Step 2, and this is a non-negotiable rule, before you even peek at your data, you have to set your significance level, which we call alpha. Alpha is just the maximum risk you're willing to accept of making a type 1 error. It's you setting the beyond a reasonable doubt bar. If you set alpha to 0.05, that's you saying, I'm okay with a 5% chance of accidentally convicting an innocent person. It's your evidence threshold. Only after you've set that in stone do you move to step 3. Go get your data and boil it all down into one single number called the test statistic. So what on earth is this test statistic? It's really just a single number that summarizes all of your data and tells you how much evidence you have against the null hypothesis. Let's really break this common z-statistic formula down. The top part, the numerator, is x bar minus mu. Think of this as the signal. X bar is just the average you got from your sample. Mu is the value that the null hypothesis claims is true. So this part just measures how far away your result is from the status quo. Now, the bottom part, the denominator. That's the noise. This is also called the standard error. Sigma is the population standard deviation, basically how much natural variation is in the data. And n is your sample size. Now look closely. N is on the bottom of the fraction. That means as your sample size gets bigger, the noise gets smaller, which makes your entire z-statistic bigger. That makes perfect sense, right? A bigger sample should give you a stronger result. So at the end of the day, this whole formula is just a signal-to-noise ratio. It tells us how many units of noise is our signal away from the null hypothesis. A big z-score means your signal is shouting way louder than the background noise. So we've gone through all that work and we have our test statistic. Now, what do we do with it? Well, we need a way to interpret it. And the first method we'll look at, the one you'll see in pretty much all statistical software, is the p-value approach. This method answers the question by thinking in terms of probabilities. There's a famous little rhyme that perfectly captures the decision rule here. If the p-value is low, then null must go. But what is a p-value? Okay, the p-value is a probability. More specifically, it's the probability that you would get a result as extreme or even more extreme than what you actually saw in your data if the null hypothesis were actually true. Basically, it's a surprise factor. A tiny p-value means your result is super surprising if the null is true, which is pretty strong evidence that maybe the null isn't true. The decision then becomes a really simple comparison. You take the p-value that your data gave you, and you compare it to that alpha level you set way back in the beginning. If your p-value is smaller than or equal to your alpha, like in this example, a p-value of 0.03 is definitely less than our alpha of 0.05, it means your result has crossed that reasonable doubt line you drew. It's just too unlikely to have happened by chance. So you say, I have enough evidence, I'm rejecting the null hypothesis. But if your p-value is bigger than alpha, then your result isn't surprising enough. It's within the realm of random chance, and you have to conclude that you just don't have enough evidence to reject the null. All right, let's switch gears and look at the second method. This is a more traditional way of doing things, maybe a little more visual. It's called the critical value approach.
Instead of calculating a probability, we're going to define a clear rejection zone on a graph. This approach asks the same question, but in a different way. It's not about probability, it's about location. Using that alpha level we chose, we basically draw a line in the sand on the distribution of our test statistic. That line marks the point where results start to look too extreme, too unlikely, to have come from the null hypothesis. Everything beyond that line is our rejection region, so the question is just, does our test statistic land in that zone?
The decision rule here is really straightforward. That line in the sand is what we call the critical value. It's a specific score that acts as a boundary. So after you calculate your test statistic from your sample, you just compare your number to the critical value. If your test statistic is more extreme than the critical value, like 1.98 is bigger than 1.645 here, it means you've landed in the rejection region. Your conclusion, reject the null hypothesis. But if your test statistic isn't extreme enough, if it doesn't cross that boundary, then you don't have enough evidence and you fail to reject the null. So let's put it all together and compare these two side by side. This table really gets to the heart of it. The p-value approach lives in the world of probabilities. You're comparing one probability, the p-value, to another, alpha. The critical value approach lives in the world of scores. You're comparing your calculated test statistic to a boundary score, the critical value. They feel different, right? But here's the absolute most important thing to remember. They are just two sides of the exact same coin. No matter which method you use for any given test, you will always come to the exact same final decision. So there you have it. We've walked through the entire process, from a simple idea to a final data-driven conclusion. And that really leaves us with one final thought. Hypothesis testing isn't just some abstract statistical technique. It's a way of thinking critically about the world around you. So the next time you're reading a news headline or you see an ad that makes some big claim with data to back it up, I want you to ask yourself this one simple question. What's the null hypothesis here? What's that innocent until proven guilty status quo that they're trying to challenge? And do they really have enough evidence to convince you to reject it?